All right, Brooke, you may want to pause it right here and look at this. This is exploration 1. I didn't get it started because I didn't have my computer for a few minutes. Want to look at that, take a look at how exploration 1 goes, see if you can tell what's going on there. And if not, we can discuss it later. But we are now going to do example 4, and I'm going to erase this. So.
That's why you don't miss school.
Okay. So jumping down to example 4, and again, the paragraph before it, so that you can kind of see where we're headed. It says, a change of variables, that's kind of what we did a second ago. A change of variables can often turn an unfamiliar integral into one that we can evaluate. You want really? You just change the variables? No, you got to do a little more than that. The important point to remember is that it is not sufficient to change an integral of the form f of x dx into an integral of the form gu dx. It is, what did I say? Did I say it was necessary?
Not
One thing is not sufficient. Oh, it's not sufficient to do just that. The differential matters, the dx matters. A complete substitution changes the integral from f of x dx to g of u du. You have to change it entirely. So the first one that we're working with here, example 4, don't turn a page. Don't turn a page. Example 4 says to integrate sine x e to the cosine x dx. What did I say, sine x?
Sine x
E to the cosine x dx. So this is a function written in terms of x, and we're dxing it, so that matches. That's good. Except for, everybody got any idea how to tackle that with the knowledge you have right now? The answer is no.
to have the product rule dealio.
Here comes the substitution. Listen. Watch what happens. It's really slick, especially with this first one.
Oh, I see. So
The trick, the thing that you have to do and use some ingenuity and a little bit of creativity is you got to know what to let u equal. And I happen to know what you have to do because I've done it for many years. U equals the cosine of x. Then what is du? Now be careful how you answer that. What is du? Negative sine x dx. Remember that separation of differentials we did before?
Oh, yeah. No.
All right, then let's backtrack here a little bit. What's the derivative of u with respect to x?
Negative sine x.
Negative sine x. Then what is du? By cross multiplying? Negative sine x dx.
Oh, I get that.
You do follow that?
Oh, so
Okay.
we could take away the dx and the sign at the same time, but the sign would have to be negative. But we could slap a -1 on there.
What are you
Will you stop talking for just a minute? You're talking, you're thinking out loud, we're not following you.
Or you're in a different world.
Listen. Shh. Wherever there is a cosine in our integral, wherever there is a cosine in the integral, we're going to replace it with what?
Negative sine x dx?
No, u.
You what? Sorry.
Just
yeah.
Wherever there is a cosine in this integral, we will replace it with u because of what we let it be up here. You with me?
Yeah.
We're attempting to change this integral to something written in terms of u instead of x by the substitution.
How did we know u is cosine?
We made that up.
That's the part that takes some cleverness and some thinking. And the more you see and the more you practice, the more it will occur to you what to let it be. I'm going to give you some tricks along the way. So just trust me, that's what you want to let u equal in this case. You will get better at deciding what to let u equal as we go along. Okay? So it's going to be a little uncomfortable for you for a few minutes until we start to get some tricks and some things. So if you let u equal cosine x, and I'm proposing we do that, then every place there is a cosine in my original integral, I'm going to replace with a u. And look at this. Every place there is a sine dx, both of those together, and the dx, that's right there. I know there's a negative, I'll deal with it, hang on. I'm going to replace that with, actually I'm going to go one more step, I'm going to replace it with negative du. Sorry. Okay, so the objective was to find something that has a dx with it that I can multiply dx by, that's also in here, and I can replace the whole product with negative du. So what I have now is the integral of e to the u, du, with the negative out here. Look how much easier that is to do.
Why do you need the negative out there?
Because it's a negative du. Here's my negative du, and here's my e to the u. Y'all see it? And because negative is a constant, I just stuck it out front.
Oh, and that's just.
This integral's easy. What's the integral of e to the u? E to the u
Plus C.
plus c. Now, do I have to make this a negative also? No, because we don't know whether c is positive or negative. You can always just put plus c. We're just adding a constant. That constant may be positive or negative. We can't tell. So you could do this if you want, although nobody does. Everybody always just adds c.
Minus C could be faster though, because I want that.
You think you have to distribute this negative for everything? You don't. It's just plus c, and this may turn out to be positive or negative. We don't know. It just depends on where you put it vertically. But we're not done because we were supposed to integrate with respect to x. So what we do is we come back
We put in.
and put what u is. This is this thing's integral with respect to x. So we come back and rewrite the u with what it's equal to, cosine x.
So could we do that without having to make the U?
Only if you're really, really, really good at this. Just to prove to you folks that this actually is, if I derive that, negative e to the cosine of x, if I derive that, I'm going to get negative e to the cosine of x times the derivative of this, which is negative sine x, and the derivative of that is 0.
What about the sine of x?
What?
Don't you need the sine of x in the front?
Sure. I'm just saying it's the same.
Wait. DX.
It is the function that we antiderive, if you take that derivative. So this is it, and we use u substitution to get at it.
Where does the DX come
It tells you what you're deriving or integrating with respect to.
in? How does it come in on that?
Oh, you got it.
What?
U to the U, guys.
Right there. It shows up right here. When you take the derivative of u with respect to x, it shows up over here, and that dx is the same as this dx times that sign. All comes together and is written in terms of u.
Oh, okay.
All right. Let's try another one. Turn a page, see if we were right. Amazing.
Incredible.
Let's try another one, and it will start, as you see more of these, it will start to occur to you how to decide what to let u equal. That's for Mariah, it's all for the rest of you as well. So let me get rid of this.
I just love this so much.
C. C for cost.
So here's what I've got now, and this looks really complex and awful. But it turns out it's a really nice one to introduce this stuff to you. X squared over the square root of 5 plus 2x cubed.
It's X squared. The first one.
This one?
Yes.
Good thing, because it wouldn't have worked otherwise. All right. So what you need to start looking for is something in this integral whose derivative is a form of something else in this integral.
That would be X squared
Say that again. Can we take the square?
Listen, you gotta look for something in this integral, some function, or some piece of a function, in this integral whose derivative is something else as a multiplier in this integral.
So
let's say,
so it's 2x
cubed.
cubed x squared.
2x cubed's derivative is something involving x squared, right?
Yeah.
But wouldn't it be better, I'm just thinking about this, if we let it be 5 plus 2x cubed, because the derivative of 5 will be 0.
Yeah.
That way we can let it be the whole mess.
What about the square root? No.
We'll
root
be integrating root u when we get there.
Yeah.
Yeah, that's okay, we can integrate root. So what we do is we let this, so that its derivative will be some form of an x squared. We let the whole thing, as much of it as possible. If it's got a constant, I recommend you let that be part of the u. So I'm going to let it be 5 plus 2x cubed. Then du will be what?
Wait, could we make it 1/3 cubed so it comes out easier?
Nope.
No, 1/2 x to the 4th.
What is this thing's derivative?
1/2 x to the 4th.
6x squared.
Hold up. What? I was a dx.
Yes. Not bad.
Do you see how this happened? You got to remember which direction you're going. You're not anti-driving, you're driving. We're deriving. In this step, we're deriving. Got her?
What? Why are we deriving or trying to?
Because I'm trying to find a du that has something with a dx in it.
Okay.
And du is a derivative. Piece of it, right?
Yeah.
We're deriving.
Yes.
All right. Now, you notice that when I get the du, up here I have an x squared, but I don't have a 6. So I'm going to continue solving this until I have this and this. I need this, and it will be replaced with this.
Okay, that's cool.
And this will be replaced with this. So what I end up with is the integral 1/6
Okay.
du
du.
square root of.
U.
That's not hard to anti-derive once you get it to here.
What happened to the x squared?
The x squared is
The x squared dx was replaced with 1/6 du because they are equal. And this was replaced with u, but not the square root, just this, and here was u. Now, shh, listen, without wasting a line, I'm going to say that this is 1/2. Now, can you anti-derive that?
Yeah.
What is it?
2/3 u to the 3/2.
Did y'all follow that? Everybody follow that anti-derivative?
No.
Yes. Wait.
Yeah.
I'm getting there.
Do you understand that part?
Yeah.
Then I must put something in the front so that when I derive this and multiply this times this, I get 1.
Okay.
So it is the reciprocal.
Got it.
So
Do you see?
Makes sense.
Everybody clear? Okay. Here's the 1/6 out here.
then it would be.
Does the 1/6 affect the c? No, it doesn't, because 1/6 of a c is still a c. You know what I mean? 1/6 of a constant is still a constant. So we're not going to put the 1/6 out here. We're going to leave the c, just c.
We can just slap C.
Yep. This times this will be what?
1/9.
What?
1/9.
1/9.
Yes.
Parentheses. Shh. 5 plus 2x cubed to the 3/2
Okay.
plus c. That is that one's integral.
Oh, that's tricky.
Whoa. So it's just like kind of like
That's a lot of
replacing
different
something,
numbers.
and then just like we're gonna put that in there quickly, just to make it easier, and then driving it, and then it's like okay, since
And then
that's
come back.
equals that, it's like we're gonna put that.
It's an awful lot like solving a system of equations. You solve it for one variable, then you take that value, plug it back in where you started for that variable, and solve for the other one. It's kind of like that. This is a substitution, but then this is a resubstitution, so that it's written in terms of x at the end. If it's offered to you in terms of x, your answer has to be in terms of x. You understand?
Yeah.
Let's try another one. Keep learning some more tricks there. Example 7 says to integrate the cotangent of 7x. Yikes.
7x.
Don't look at the solution.
I'm not.
My eyes are tempted, but not.
Yeah, don't do it. It's the integral of the cotangent of 7x dx. That's what we wish to find the family of functions whose derivative is this. This is where all those studies that you did in trigonometry with identities is going to come in handy for you. Because we don't know of any particular function whose derivative is cotangent, but we can rewrite cotangent in terms of things that are derivatives of each other.
Cosine over sine.
Yeah.
Yeah.
So this thing's going to be the integral of cosine 7x over sine 7x dx. And that's just a renaming of this using an identity. We haven't done any integrating or any substituting or anything. It's just a rewriting of an identity. Now we know that sine and cosine are integrals of each other. I mean, derivatives of each other. So what do you want to let u equal in this case?
Cosine. That's how it is.
Okay?
Why cosine?
That's everybody's first instinct, and that's okay.
I was thinking sine.
Just this.
Underneath.
Shh. Shh. If you let u be cosine, think about the process that I showed you a minute ago. You will have your du in the denominator. That's always dangerous. You want your du to be in the numerator.
So sine.
So if we let it be, this is a trick I'm teaching you about this. When you have a quotient, you're anti-deriving. Best bet, if you can possibly make it work, is to let u equal the denominator, so that the numerator can be part of the du. Okay. So if I let u equal sine 7x, then what is du?
Negative cosine, 7 negative cosine, negative 7 cosine.
Cosine 7x times 7
Negative, no, not negative, why?
dx, right?
Would it not be?
No, no, because it's sine and cosine.
It's
Sine to cosine that doesn't have a sign change.
Yeah.
We're deriving sine and getting cosine. Oh, we're applying the chain rule, that's where the 7 came from. Everybody clear? Now, look at what we're anti-deriving. I have a cosine 7x dx, and here it is. Cosine 7x dx. That dang 7 screwing things up, so I'll go one more step. So this thing right here becomes 1/7 du.
So we have 1/7 sine 7x du.
We have 1/7 because that's a constant
Oh, yeah.
integral of du over u. Sine x is u. Sine 7x is u.
Which is 1/u to u,
It is.
which is u to the -1, which is natural law, which integrates.
Thank you, Sam.
We're so freaking
Do you understand how we got from here to here with this? Everybody clear? Then I'm going to rewrite this as Sam's recommended so that we can recognize it a little bit better.
Oh, yeah.
The antiderivative of 1/u is what? Is log u.
Just log u though?
Just log u.
Just like.
There's a 1/7 out here plus c.
Oh, because log u times, just log u times the derivative of inside is it does.
So 1/7 natural log of sine 7x plus c is the antiderivative of that. Can you see the substitution working here? Is it necessary? Can the sine of 7x ever be negative?
Sure.
Yes.
Yeah.
You must leave those on there.
That's just. wait.
That way you don't have to restrict it on that. Whatever x is, we force it to be positive before we log it, so we don't have to restrict it on it. Y'all clear?
Yes.
If you were to derive this, which I'm not gonna do, if you were to derive this, you'd get cosine 7x over something. You'd get this if you rewrote it, but then I did it.
Let's see. Yes, that's what.
So, did you catch that? On this one, we had to rewrite it in terms of things that are derivatives of each other, and then we choose the denominator so that the numerator can be part of the du. We want du to be a multiplier, not a divider. Du should never be a divider. That makes all kinds of troubles.
Can you just put like, can you just take it out like that and then do like du to negative?
You cannot take anything out except for constants.
So like, you'll like not take it out, like take it out as a fraction, put like the du, and then you just put like with that case, u to the -1.
It would have to be du to the -1, and nobody knows what that means. Just dodge that one.
Okay.
No.
Yeah.
Okay, shh, let's try the next one. Well, there's actually 3 we're gonna try now. We'll do them one at a time. Please don't look at the solution on the next page. Don't do that to yourself. You'll learn a lot more if you follow this and help you to make decisions. Then when you make them for yourself, you'll be ready to go instead of just looking at a solution. So what I've got next is dx over cosine squared 2x. It's the integral of dx over cosine squared 2x. That's the integral I want to get done. Can you think of anything you'd like to let u be? The answer is not yet. Not yet. Let's use another identity and rewrite this first. What's a rewrite of this?
Secant squared of 2x. Yeah.
Yeah.
Oh, yeah.
And we know somebody whose derivative is secant squared, right?
Tangent.
Tangent.
So we don't even have to
So-
do those.
We do. Well, if you really want to follow through on what we're learning here. Shh. Listen. Shh. We do know someone whose derivative is secant squared x. But what about the 2x?
Can you not?
Is it just like a chain rule?
Yes, but you have to be able to account for it carefully. And people that are reasonably clever can do this without a u substitution. But I'm going to do a u substitution to show you it works. Okay? Since I already know someone's derivative is secant squared something, I'm going to let u equal to 2x. What's its derivative?
2.
2 dx.
I'll look at
Well, I want to just replace dx with du, so I'm going to have 1/2 du equals the dx. And that's your chain rule. that you were talking about.
That's what
Accounting for it with a 1/2. And you don't have to do this in this case if you understand how to account for it. Because I did, here's what I've got. I've got 1/2 on the outside. du is in here.
Sure.
That replaces only the dx. That dx is only equal to 1/2 du. And then I have the secant squared of u.
Oh, that's funny.
That allows you to keep track of your 1/2 and your 2s and your all kinds of stuff like that. So now we antiderive that and we get tangent of u with a 1/2 on it plus c. And that is 1/2 tangent of 2x plus c. And so you're right, you can come up with this 1/2. If you understand the chain rule, and you got to have a reciprocal to account for it. That's fine. But this is how the u substitution would work.
Oh, is that secant squared of u?
Yes.
Oh, I thought it was times u. I was like, where the heck?
Well, there's be no variable.
Yeah, well, that's why I was confused, Axel.
Yeah, I separated it too far for him to see what we're doing. What?
So we're trying to set up something that gives me antiderive.
And if when you rewrite this cosine squared as secant squared, and you recognize secant squared as someone's derivative, don't let u equal secant squared. Because we already know an antiderivative for secant squared is tangent. But if you got some other function of x back here, you might want to let that be. So that you're actually anti-deriving secant squared of a single thing instead of 2x, unless you can account for it with the chain rule like you do. This keeps track of things for you.
Where would you?
I just don't know how to use it.
Okay, here comes the next one. You ready? Next one is cotangent squared 3x.
Yeah.
Cotangent squared 3x dx.
Which water bottle is this?
Now, do you know of someone whose derivative is cotangent squared?
No.
Me either.
But sine squared over.
Do you know of an identity someplace that we can rename cotangent squared? Because that seems to be the theme for.
Oh, it's cosecant.
Look it up.
This makes me
1 plus cotangent squared of x equals.
Is it a
Cosecant squared
secant?
x.
No. So then 1 minus cosine.
So cotangent squared is equal to
Cosecant squared x minus 1.
cosecant?
Oh, this. Let's look at it.
Is it cosecant?
Wait, no, it's
Is it? Check it out. What's the Pythagorean identity belonging to? Cotangent squared.
cosecant squared x.
Cosecant squared x minus 1.
So this gets replaced with cosecant squared x minus 1.
Yes. Would it be 3x?
Oh, yes.
You just gotta go back. So it'd be 1 sine squared.
So this one's now a Pythagorean identity. Why do you suppose we wanted to choose this? Because we know someone whose derivative is cosecant squared.
Did we just do that? No, we didn't see it. No. That, wait. Cotangent.
Do you know someone whose derivative is cosecant squared? Can you also understand that we can do this
Yes.
and deal with this with the u substitution and this because we know how to antiderive a 1?
Can you do that?
You bet.
Yeah,
Wait, why?
because back in chapter 4.
If you're integrating several terms, you can integrate each term separately. Terms. This is f of x plus g of x.
So was the d of x times the whole, it was because we had the print.
It was dx for both. It goes to both integrals, as long as they're both written in terms of x. All right, so I'm focused on this integral. I'll come back to this one in a minute. This one's easy. This one's going to need maybe a u substitution. What should I let u equal if we're just going with the idea today?
3x.
U equals 3x. Du is? Can I do this?
Yeah.
You getting used to it enough to understand this? Okay. So I'm going to rewrite this integral as what? Using that u substitution.
Wait, what? Say that again.
I'm rewriting this integral with this u substitution.
Cosecant squared
Of
of
u.
u 1
Of
u
1/3.
1/3 in front of it. The whole thing.
You okay with that?
Yes.
Minus the integral of 1. I'll deal with that in a minute. I just want to leave that alone. I know what I'm going to do with that one. That's not a hard thing.
That's x, right? You need the
Yes, just x. Okay. So whose derivative is cosecant u? Cosecant squared, excuse me. Whose derivative is cosecant squared?
Negative cotangent.
Negative cotangent?
Yeah.
So this is negative cotangent u 1/3, oh, I have to put the negative up, put it up front. You okay with that?
Yeah.
Plus c on this one minus, what's this?
X.
X?
Plus C.
Now I've got a u here and an x here, but we'll come back and replace this, right?
Wait.
Don't worry about it.
No.
I have to anti-derive with respect to x, which
Yeah,
is,
yeah,
this is
yeah.
1, this is x,
Keep going.
plus c, right?
Yeah, that's.
Okay, so now I have negative 1/3 cotangent, 3x minus x
Plus
Plus
2C.
2.
plus c, all one together. These are not the same c. But if I add them together, I'll get another c.
Yeah, because they're just constants, and you have a bigger
They're
C.
just constants. They don't behave like variables, they're just constants. If you add a constant to a constant, you get another constant. Even if it's 0, it's still a constant.
Constant.
I wish this was vodka.
Okay? So if we were to anti-derive this, we would get back to this.
It's gotta be on our shirt.
We got that.
That's
I
gotta
wish this was fun.
be on our shirt. I don't think that's allowed.
C is just a constant?
No,
I wish this was vodka.
Okay, did you follow that one all the way through? What we did is we actually used a Pythagorean identity, which came up with a piece of it that already had an antiderivative, but we were anti-deriving a function, so we used the substitution over here. It was a short little thing.
That
Kinda
was just the A part.
I'm crumbling.
Well, that's the B part.
Oh, that was the B part.
The C part is cosine cubed
But I'm also halfway done.
dx. The integral of cosine cubed dx.
I've just developed that.
Water raisin.
Cosine cubed X. That sounds
You can make decent wine by setting that the.
So cosine of X cubed.
Yeah, to the past, then.
No,
That's
it's the
the same
cosine
thing.
x. It's the cosine of x, all cubed.
That's the same thing, right?
Oh, that hurts.
So could we use cosine X as U?
Its derivative would involve a sign, which I don't have.
So negative cosine.
Can we pull out a
Can you use the
cosine
power
X?
rule?
Can we pull out a cosine X?
Because it's cosine cubed, and cosine is the inner function whose antiderivative will have to, and there's no sign in this thing anyway. Be nice if there was.
So we're trying to solve this. Is that what we're
Hint,
doing?
hint, hint.
So
Change it into sign.
What? Do you have a replacement for cosine
Can we
cubed that
take
involves a
out?
sign?
Can we take out? Can we make it cosine squared times cosine? And
Yes.
Cosine X times.
You can.
Okay, well screw you, Jose.
So if we do this, and I call that cosine squared, which is something we're a little more familiar with times cosine, that's another rewrite of it. We can do that. That's still the same thing. Now what?
you make cosine squared sine X squared, sine squared X minus 1.
What? Other way around.
I agree.
1 minus sine squared X.
Yes.
One minus sine squared.
So we replace this one with 1 minus sine squared. Cosine's still sitting out here. Now, do you think we might have what we want, or do you want to integrate that cosine through there and integrate two separately? Do you want to just do a yes substitution now? What do you think?
Let's just do it.
If we made.
Do you want to do, what I'm saying is, do you want to distribute that? Or do you want to do a U substitution now? What do you think we should do?
Substitution now.
Whoa.
And if you do the U substitution now, what will you use for U?
Negative sign.
Kennedy to come to the office.
Who has to go?
Sine X.
Just wait.
Sine X.
This is, oh wait, I'm gonna wait.
We make
Let U equal sine X?
Yes.
Will that help? Let's see.
Yes, because U equals cosine X dx.
Oh, yeah, I can see that now.
Can you see the cosine X dx?
Boom.
So this becomes what? Use this U substitution, this becomes
1 minus U squared.
Minus U squared.
Du.
Du.
and there are two terms we can integrate separately. What's the integral of one?
What?
We're integrating with respect to U, so for right now, it would be U. See, we're integrating, that's where it becomes important. We're integrating with respect to U, so if we integrate one with respect to U, it is U, not X, U. Are you with me?
Minus 1/3
Minus, what's this one's integral?
1/3 U cubed.
1/3 U cubed plus all the c's involved with all the integrals we
Plus
did.
constant. That's antiderivative.
And so the answer is?
Sine x.
One
third
third
sine
sine
x
cubed x. Oh my gosh.
plus constant.
There you go. You see what's happening here?
Yeah, but
Now, just so you understand, shh, had you decided to distribute that cosine before you integrated, it still would have worked out. But you would be integrating cosine, which we have an antiderivative for already. And then you could use the u substitution on sine squared and cosine, just like we did there. If we had that other integral. So you can distribute, still use the same u substitution, it'll be fine. Or you can leave it like this and let this whole thing. Actually, could I have let that whole thing be u? I could have let that whole thing be u. Would it work out the same?
Let's try it.
let's try it.
Let's try it.
Because
Okay,
the
so this
derivative of
This is what I'm trying to integrate with a different u substitution, which is 1 minus sine squared cosine. And if I let, in this case, if I let u equal 1 minus sine squared, all of it, since the derivative of that is 0, what would I get? du is,
U would be negative.
du is
One half
squared.
Half du is negative.
It would be negative two.
yeah, this isn't gonna work, is it? This
I
u
don't think anything
substitution
has
won't
sine
work.
squared. Sine, no, we could do it, do product rule of sine.
No, not product rule. How would you, what's the derivative of negative sine squared? Just tell me what that is.
Well, no, when we rewrite negative sine, that's a good question. It would be negative 2 sine x cosine x, yeah.
Well, so you can do the power rule with that.
But we don't have a leftover sine x to go with this cosine x dx.
So could we solve that for like x and then plug it in and do some shenanigans?
MJ,
Yes,
is Connor able to come to the office?
I'd rather have him for the rest of the hour, but whatever.
Sounds good. Have to stop between classes. Thank you.
Okay, all right, thank you.
Since we saw that, like, it was urgent, Connor.
You may be able to force this to work, but this is far easier.
Yeah.
So what we look for in here is something in here whose derivative was something else, and the derivative of this piece, one piece of the sine, the derivative of that was one of these, just the sine part, so this ended up being u squared. We can handle that, we've got a power. Okay, so this was not a good idea. Okay, now, let's try another one. This was all about the trig stuff. Next one's rather interesting, but the next one's actually a definite interval. So we're gonna use a u substitution to get it done. We have a definite integral, we're gonna use an indefinite integral to recover the function and then integrate.
0 to pi thirds.
So, what does the integral say?
0 to pi thirds, tan x.
Secant squared. Riemann.
Okay,
Yes.
do you see anything that's presented the way it is, whose derivative is something else in this thing?
Secant and
What do you wanna let u equal?
what?
Tangent, because the derivative of tangent is? Secant.
X squared. So we just turn it into u du.
So we have u equals tangent x, and du equals secant squared x dx. It's all there. This whole thing gets replaced with du, and this gets replaced with u. However, there's a problem, folks. There's a problem here. When you write that down with the u substitution, we have u du. This is no longer 0 to pi thirds.
What?
This will change variables. We've changed what we're doing. It's not 0 to pi thirds anymore.
It's x to u.
Let me show you two ways to handle it. You're gonna have to know how to do both ways. Both of them. Listen. Don't put the limits of integration. When you change variables, you leave the limits off until you get back to where you've written in terms of x. Then you can come back to these. So leave it with no variable, with no limits of integration. What is the derivative of this?
1/2 u squared.
Plus c.
Okay?
Wait, what?
And what's this gonna become?
It's just 1/2.
One U.
So what do we get?
We get 1/2 tangent squared plus c.
We don't have a plus c because we're coming back to the definite integral and going from 0 to pi thirds. We don't need the plus c because this recovers a family of values. This finds an area under the curve. So I really didn't need this since I have a definite integral to begin with. But you can put it on there because I left them off there. So technically you need that. But when you come back to putting it in terms of x, you come back to the limits of integration.
I'm okay with that.
Stop talking. Now we evaluate and we get 1/2 parenthesis What is tangent squared of pi thirds? Tangent of pi thirds.
Tangent of pi thirds is like root 2 over 2 or something.
It's root 3.
For the 3 over 2 over a half, which is for 3.
What's the tangent of 0?
Wait, so
0.
it's squared. But it's squared.
Undefined?
But it's squared.
Well, it can't be
You're right,
undefined,
so we
it's
get
always 0.
this.
3.
Minus
0.
0. So the answer is 3/2.
Can you do that?
Yes. Now let me show you something that you're gonna need. You have to know how to do it this other way as well. I'm gonna rewrite this over here, this part right here. I have the integral of u du. It is possible, and you should do it. You should practice both ways. To put limits of integration here, but they won't be 0 and pi thirds. They will be u of 0 and pi thirds. What is, if I come up here, what is u of 0? It's 0. What is u of pi thirds?
Root 3.
Root 3.
So it's 0 to root 3.
It's 0 to root 3 is what we have to integrate.
How do we do
That changes our limits of integration. You have to u the original ones to come up with the u substitution replacements.
And now would we just?
Now we
solve it
integrate
like
and
we
never
would
come
if
back to
it was
x. We never come back to x since we changed these. So it's going to be 1/2 u squared evaluated from 0 to root 3, which is 1/2 times root 3 squared
minus
minus 0,
0.
which is 3/2.
Wait.
I know, it's awesome. Okay? Did you follow that, Axel, or not? Yeah?
Well, we have a lot of.
If you change the limits of integration by u-ing the originals
That's just
and put them here, then you can stick with u through the whole evaluation. You don't have to come back to x. What?
That's just another way.
That's another way, right?
This is the better way of doing it, and they will test you on this.
Well, that's easier.
They will test you on this. You can't say, well, I like this better, so I'm not even gonna learn that. No, you have to know them both.
That was easier.
It is usually easier. But you have to u it first. You still have to evaluation of it first. Okay?
I have nothing to do with that.
All right. We're just about out of time. We only have one example left. I'll do it for you tomorrow, but you got plenty to get started on this thing.
It's so long.
Finding the u is what's gonna be trouble for you. Keep trying it out. If
They
you
just
don't
like you.
take it, then.
This reminds me of proving trig.
Oh, yeah.
Oh, you have to remember your trig, that's for sure.
That brings
Hope you
back
got enough to
some
make
fun-
some
That was
progress, yeah.
being,
You try like 20 different times before you found